All right, hello calculus. This is lesson 6.8, accumulation plus Riemann sums. So today sort of takes us all the way back to the beginning where I talked about the meaning of calculus and where we're going. And like the very first lesson back in chapter 1 was a great little lesson that sort of gave you an introduction to what accumulation and an integral really means. So accumulation refers to sort of the accumulation of area. And we know now that that's what an integral represents. It's the area under a curve. When it's bounded, we can find that area. And so we're going to do a little bit about that and use it to help us analyze a function. It's kind of lots of going on here. And then we're going to talk about Riemann sums, which is just that easy approximation of finding area. So example 1, now this is from AP Classroom. I've shared this document with you. So you might be able to find it. I don't know. I did some cutting and pasting here, but you might want to pause and copy down the graph. Give yourself a good space to do it in. We want to use this graph of f that they gave us to graph the g function. And we know that they're telling us that g of x is the integral from -1 to x of f of t dt. And that's what this function we're looking at is. This is f of t. And so remember, whenever you see an integral, especially one with boundaries, it really means the area under the curve. And in this case, that curve is a bunch of straight line segments, which means we can use some triangles and rectangles to approximate the area. So I'm looking at this lower boundary, and the lower boundary is -1. I'm actually going to start there. And what I'm going to do is basically think about areas, try to figure out how I can actually graph ordered pairs for our g function. So I'm going to start with that. I'm going to start with -1. So if I plug in a -1 for x, then that would be the integral from -1 to -1 of f of t dt. Now, don't just always think the integral. What does the integral mean? It means the area. What is the area under the curve from -1 to -1? There's not much area in a single point. So it is 0. So I'm going to go ahead and just graph g right on top of my f of t function here. All right, let's try another one. Let's actually try not -1, but 0. So here's 0, and we're going to plug in 0. So the integral from -1 to 0 of f of t dt. So again, this really means the area under the curve. So from -1 to 0, what is that area? Well, it's 1/2 the base times the height. The base is 1, the height is 1, and so we get 1/2. So this area is 1/2. And I wrote that in because I think it's kind of nice. I'm going to use a different color though. So I'll write it in as 1/2. But it's actually an ordered pair of our g function. So the point 0, 1/2 is a point on our g function. Kind of interesting. Then let's try if we plug in a 1 for x. So that's going to be -1 to 1 of our f function here. So again, it's asking what's the area from -1 to 1. Well, it's another triangle. That'd be 1/2 the base of 2 and the height of 2. So that would be 2. All right. I'm not going to write in 2 is the accumulation of areas. Do you see that? So it's 1/2 plus 3/2, I guess. But I'm not going to write that in. That just seems confusing. All right. So now we can try a 2, plugging in a 2. Oh, I need to plot that point. It's 1, 2 for my ordered pair. 1, 2. All right. And now we're going from -1 to 2 of my f function here. So from -1 all the way to 2, what is the area? Well, we know that that whole triangle from -1 to 1 is 2. So that was the area from before. Plus, we just need to add in this rectangle. So that's a base of 1 times a height of 2. So that gives me 4. So my ordered pair would be 2, 4 for my G graph. There. All right, G of 3 would be the integral from -1 to 3 of f of t dt. And again, all the notation is monotonous. I get it. I'm lazy also. But you must be used to it for the AP test, all right? Lots of notation. And if you have the notation, you will earn points. So from -1 to 2, we knew that the area was 4. And so now I just need to add in this other little triangle here. So that'd be a 1/2, a base of 1, and again, a height of 2. So that gives me 5. So 3, 5 is another point on my graph of G. Whoops, wrong color. I hate when I do that. All right, let's look at G of 4. That'd be the integral from -1 to 4 of f of t dt. We know to go from -1 to 3, that's a total, an accumulation of area of 5. And then to get from 3 to 4, I need to add in this little area, this little triangle. It's below the axis, so I know it's negative. And again, it's got a base of 1 and a height of 2. So that would be a total of 4. So I have an ordered pair 4, 4. Coming back down. Let's see, G of 5 would be the integral from -1 to 5 of f of t dt. I know to go from -1 all the way to 4 as an area of 4. And so I just need to add on there my area for this little rectangle right there. But again, it's negative. And it has a base of 1 and a height of 2. So that's going to subtract 2. So we had the order pair 5, 2 for my G graph. All right. Ugh, my hand hurts. I'm cold. All right, G of 6, the integral from -1 to 6 of f of t dt. Again, we know to go from -1 to 5. That's an accumulation of area of 2. And so now we want to see how much more area if we go to 6. So I need, interesting here, got a couple of pieces here. I see a little triangle and I see a square. So, okay, well, I can add up a lot of areas. I know this area is 1 by 1, which is 1, and this would be 1/2 of 1 times 1, so 1.5. So we're going to subtract that, 1 and 1/2. So we just get 1/2. So we have 6 1/2 for a point on my graph of G. And then G of 7 is the integral from -1 to 7 of f of t dt. All right, and so once again, I have another, to go from -1 all the way to 6, we had an area of 1/2. And now, again, I have another little area here, which is another 1/2 that I have to subtract. So we get 0. So 7, 0 for my ordered pair on the graph of G. Now I'm almost done because I need to go backwards to -3, and I didn't do those on purpose. Because if I wanted to find G of -2, that would be the integral from -1 to -2 of f of t dt. Now I haven't specifically talked about this yet, but you have experienced it, and I hope that you realized it. These are out of order, aren't they? They are reversed, as in opposite. So in order to switch them around, I need an opposite on there. So I'm going to put a negative on so that our boundaries, our lower bound is actually lower and our upper bound is actually upper. So we can switch those by putting a negative in front. Of f of t dt, All right, so to go from -2 to 1, so this little space here, we know it's negative. We got a negative out in front, and it has a triangle, so 1/2 times 1 times 1. And it's negative, so it's -1/2. And then those negatives negate each other. So we get an area of 1/2, which means g of -2 is at 1/2. All right, and then g of -3 would be the integral from -1 to -3, which again is opposite. So we need to swap those around. So opposite of -3 to -1. And to go from -1 to -3, again, the area is negative. We've got a negative out in front, and I know my area is negative. And it's again a triangle, so 1/2 times the base of 2 times the height of 1. And that gives me 1. So -3, 1. So this is connecting in a nice smooth curve here. Sort of. All right. Now, it turns out that this section of our graph is horizontal, which means the corresponding section would actually be a perfectly linear line. So this is a straight section here. No curve to it. Same thing here. Horizontal line will give us just a straight section right in here. So those are linear, straight. Kind of interesting. All right, so what we're looking at here, this is our graph of g of x, which is the integral of f of x, which means f of t was our derivative, and this is the primary function, shall we say, the original function. And so we can answer all sorts of questions, and that's what we're going to do. Now, the question is, was it necessary to go through all of this accumulation of area to graph it? I don't know. It's your call. But let's answer some questions and refer back to this graph. So we want to know y equals g of x is increasing over what interval? So when we're looking at our purple graph here of g, it's where is it increasing? Well, it's certainly increasing from -1 up to 3. Whether you use brackets or parentheses is not going to matter. Consistency matters more. All right, let's see. G of x is decreasing over what interval? Where are we decreasing? We're decreasing from -3 to -1. You can see it's going downhill. And it's decreasing in this region from 3 to 7. So -3 to -1. And did I say 3 to 7? 3 to 7, yeah. Now it's asking, where is g of x concave up? G of x is concave up. Well, this is an interesting question. Concave up, so this certainly looks concave up, but the question is, where does it stop being concave up? Well, remember, this was a horizontal line. This is linear. It's straight. It is neither concave up nor concave down. It has no concavity. Really interesting. The same thing here. It is a perfectly straight section. It has no concavity. All right, so kind of interesting. So we are definitely concave up from -3 to 1. Was it 1 or -1? 1. Okay. Where else are we concave up? You can also see this section here looks to be concave up as well. And again, this segment has no concavity. That's really interesting. And this has no concavity. All right, but this section does. So from 5 to 7, it's also concave up. Where is g of x concave down? So So where are we concave down? This little section right here is a little concave down section from 2 to 4. Now here's the question we really want to answer. How can you spot a local max, min, and point of inflection of G just using the graph of F that was given to us? So this is a great sort of review, again, of local min and max. So let's look at this. And you can see here, relative min or relative max, local max or local min. Okay, so what we're looking at with our regular graph of F, that original graph, are critical numbers. And so we had critical numbers anywhere where the graph crosses the x-axis. So -1, -3, +3, and 7 are all critical numbers. You can see here at -1, our graph of G does reach a local minimum. And you can tell that because our graph of F is changing sign. It's changing from negative to positive. And that would be going from a decreasing to increasing G function. All right, so that local minimum is where F changes from negative to positive. All right, and that would be where G is changing from decreasing to increasing. Where is the maximum? Here you can see it clearly. This is the relative maximum. It happens to be the absolute maximum on this interval. And that happens again at 3, this critical number, because we're changing from, F is changing from positive to negative. That would be where our G function is changing from increasing to decreasing. So again, that maximum, F changes sign, the derivative from positive to negative. All right, so F is the derivative of G. All right, where do we see the point of inflection? This is kind of a tricky one. A point of inflection, when I'm looking at a derivative function, then the point of inflection is a relative max or min of there. So right here, this would be a point of inflection at -2. The relative minimum or relative maximum. So right here, we actually get a point of inflection at x equals -2. And this is where our F function is changing from decreasing to increasing, or vice versa. So a point of inflection is where F, I meant to just write F. F changes from, that's from increasing to decreasing, or vice versa. All right, and that's important. If it changes from decreasing to increasing, that also would be a point of inflection. Now, here is where it's really interesting, because we're going from increasing to constant. That is not a point of inflection. So we knew that this had no concavity. It cannot have a point of inflection. And here again, we're changing from constant to increasing. So we're not going from decreasing to increasing. Not a point of inflection. All right, so really kind of interesting stuff. A little bit of analysis there. Let's do a little bit more. This one also takes a little bit of time. But you'll see this in Delta Math today. The areas of the regions bounded by the graph of the function f. So this graph is our f function, and the x-axis are labeled. So you see those labeled values, area values. Let G be defined by the integral from 8 to x of f of t dt. What is the maximum value on the closed interval? Very important here. And this again goes back to our unit 4 and 5 where we were analyzing functions. This is an absolute maximum on a closed interval, and that requires the candidate test. And so this is kind of a great review, but now we're just also doing it using integrals. So the candidate test said, hey, we need to find all the critical numbers which we get by looking at the derivative, where the derivative is equal to 0. So what are the critical numbers and also the endpoints? And those were the very important things that we needed to find. And then we can test them to see which one is the biggest or smallest to get the maximum in this case. So to find critical numbers, I need the derivative function. So the derivative of g of x would just be the derivative of this integral function. Well, the derivative and the integral cancel each other out. And remember, when we take the derivative of the constant, it would end up being 0. And we need to take into account the derivative of this upper limit, which just happens to be 1, so no worries there. And we just have to plug in the x then. So the derivative of the g function just happens to be the f of x function. So exactly what we're looking at. So I am looking at the derivative of my g function, which is kind of nice. So then we can see the critical numbers are -6, -2, 1, 4, and 8. And that happens to be including the endpoints here, which is nice. So the critical numbers are -6, -2, 1, 4, and 8. And so all of these critical numbers and the endpoints, you notice we happen to be involving as well, we're going to test. And so we need to figure out what is G evaluated at -6, what is G evaluated at -2, G of 1, G of 4, and G of 8. And if we can figure that out, then we can see which one is the biggest. All right, so let's plug in -6 to our G function. That would be the integral from 8 to -6 of f of t dt. Remember, integrals mean area under the curve. And whoops, our boundaries are mixed up. So we want to reverse them. So negative integral of -6 to 8 of f of t dt. And let's see. So there's a negative out in front. And what is the sum of the areas from -6 to 8? Well, that would be a -15 plus a 10 minus a 6 plus a 5. And I think I get 6. All right. Then we want the integral from 8 to -2 of f of t dt. But again, we need to reverse that because they're out of order. -2 to 8 of f of t dt. All right, so from -2 to 8, what's the area sum? There's a negative out in front. We've got +10, -6, +5, and that area turns out to be -9, I think. Yeah. Okay. All right, now we have the integral from 8 to 1, which again is out of order, so reverse 1 to 8 of f of t dt. So negative out in front, and we want to go, what's the sum of the areas from 1 to 8? So a -6 and a 5 added up gives me -1. The opposite gives me +1. And the integral from 8 to 4, reversed, -4 to 8, f of t dt. All right, so to go from 4 to 8, there's a negative in front. That area is 5, so we get -5 for the area, for the point, the ordered pair actually on G. And then here we have the integral from 8 to 8 of f of t dt. Well, what's the area at 8? Nothing. Yeah, 0. All right, so now we just need to figure out which one is the maximum. What is the highest value here? Happens to be 6. So there you go. That's the highest value on the interval. You can see this one happened to be the maximum at the end point. Doesn't look like it, does it? But remember, we're looking at a derivative, so it's hard to tell. You'll also notice that when I'm looking at my derivative here, if we went from positive to negative, this would also be a relative maximum. And you don't think that looking here, just because of the shape of this, it doesn't change sign, but that's because it's a bounded interval, right? So I don't know what is actually happening over there. So we have to test this point. This at 1 happened to be the next highest value. So always remember to check those endpoints. They are important, okay? On a closed interval. All right, let's do, oh man. I'm gonna go ahead and stop this and start part 2, yay!